Unsuspectingly, I watched next morning as a visitor, John Engelbrecht, measured the speed of light.
I'm generating the light pulse with a sparker, which I'm going to turn on here. And that creates sparks, essentially short beams of light, that travel across to the other dome where we have a mirror. And the mirror reflects the beam of light into this telescope right here, where we have a photomultiplier tube to pick up the light signal so that we can look at it on the oscilloscope right here. And we measure the time interval by measuring the distance between the two blips on the oscilloscope, where distance across the screen is time.
Looks like about 450 nanoseconds.
And the round trip distance is 134 meters.
Yes. Well, it's not bad. You've determined the speed of light this morning to be about 298 million meters per second. An accuracy of about 1%. The speed of light is, in fact, Peter, known to great accuracy. It's one of the most precisely known numbers in all of physics. The National Bureau of Standards in the United States has a figure of about 299,792,457.4 meters per second.
0.4?
Well, the National Physical Laboratory in London perhaps would disagree with the last figure.
Oh, yes, I thought so.
Einstein was emphatic that the velocity of light is always a constant, no matter what the motion of the source or the motion of the observer. I've checked this, in fact, using not light, but X-rays, which are a form of light, but at very high energies.
They're scheduled to land.
In 1970, a satellite was launched off the coast of Kenya for the purpose of doing X-ray astronomy. It was called Uhuru. It discovered and began observing a peculiar class of star. An X-ray binary pulsar gives off regular bursts of X-rays while orbiting at a high speed around another star. Now suppose that Einstein were wrong, and that X-rays go faster if they're launched when the pulsar is moving towards the Earth. Then X-rays from that part of the orbit could overtake X-rays that are coming from the other part of the orbit, making a simple picture quite complicated. For example, you could see the pulsar coming and going at the same time.
Yeah, it says it's all time. I know they got on the plane.
Peter, from my friend Ethan Schreier at the Smithsonian Astrophysical Observatory, who worked on the Uhuru satellite, I got the following tracing of X-ray pulses coming from the X-ray pulsar Centaurus X3. And as you can see by looking at these pulses, they're absolutely regular. Each pulse comes along at a specific time interval, and there are no spurious ghost pulses lying in between the pulses that we see here. This is direct proof that the speed of light is indeed independent of the velocity of the source. I looked at three separate sources, the most distant one lying in the small Magellanic Cloud.
Okay.
The light took 200,000 years to arrive at the Earth from that source. And in all that time, the pulses emitted when the pulsar came towards us never overran those that were emitted when it went away by more than a factor of perhaps a part in a billion. Well, to put it in earthly terms, that would be about the speed of a turtle moving along the ground.
That's a very earthly term.
Right.
In deference to this evident obsession of Einstein's, I accepted that in cosmic space the speed of X-rays, or visible light, or radio waves, never varies. But, dear me, how promptly that golden rule was broken.
If we send radio pulses to another planet like Mercury or Venus, when they're on the other side of the Sun from Earth, they can appear to be slowed down by the direct effect of the Sun's gravity on the waves as they pass near the Sun.
It looks from where we are as if the Sun's gravity acts very like a lens, bending the light and slowing it down.
About 15 years ago, it occurred to me that this increase in the travel time was a direct consequence of Einstein's general theory of relativity. In those days of increasing science budgets and low rate of inflation, it took less than 2 years to convert that idea into a very sophisticated radar system, which we installed on the Haystack telescope to make these measurements on Mercury and Venus. Now, the actual predicted effect is very small. It's only 200 millionths of a second out of a total round trip time of about 1,500 seconds, or approximately 1 part in 10 million. And we were able to measure it with an accuracy of approximately 5 or 10% with this radar experiment. Now, if we could turn to Mars.
You can't expect a very good image of Mars just now because it's right on the far side of the sun and it's close to the horizon, but maybe we'll get an impression.
Mars is now very near the far side of the sun as we view it from Earth, and is in a good position to see this effect. And in fact, the last time Mars was in this position, we used radio waves sent to the Viking spacecraft, which were landed on the surface of Mars, to measure this predicted slowdown much more accurately. And with such measurements, we were able to verify the predictions of general relativity on regard to the slowdown to an accuracy of about 1/10 of 1%.
Okay, you say light slows down near the sun. But Kent Brescher told us just now that light seems always to go at the same speed. I think, Peter, that as a theorist, Roger Penrose here might resolve that contradiction for us.
Yes, well, you see, it really depends where the measurement is done. If you measure the speed of light as it appears at the surface of the sun from here, then it would seem as though it slows down. It would seem as though the sun was surrounded by some sort of lens that should not only slow the light but also bend the light. Whereas if you did the measurement at the surface of the sun, then you would get the same answer for the speed of light as you get for the speed of light at the surface of the Earth.
We had come to the nub. To keep his blessed speed of light always reading the same, Einstein decided that time itself must slow down near a massive object.
So gravity has the apparent effect of reducing the speed of light and slowing down time. So that if you imagine the extreme situation of a black hole, then light would be reduced to 0 speed, apparently, and time would apparently have been stopped completely at the surface.
Apparently. Well,